So in the last lesson, what did we do? We found that the variance of the sample mean is the population variance divided by n. Okay, so you might be looking at that and observing that as n goes to infinity, the variance of mn goes to 0. Okay, so as we get more and more data, that estimator mn of the sample mean is just there's less and less variance of it, so it is ending up closer and closer to its true value. This kind of idea and this kind of question about what happens to estimators as the amount of data gets infinitely large is the topic of asymptotic theory. And so that is just how estimators behave as the number of observations goes to infinity. So that is as we get more and more data. Okay. And the kind of the main asymptotic property that we want our estimators to have is consistency. So we're kind of like doing some definitions here. And the definition of consistency is that estimator G of X, okay, statistic G of X, so an estimator is a statistic, is a consistent estimator of unknown quantity gamma if the following thing is true. The limit as n goes to infinity of the probability that the absolute value or the distance between the statistic and the unknown true value, the probability that their difference is less than epsilon is 1 for all epsilon greater than 0. Okay, so this is one of those kinds of definitions involving a limit where it makes sense to think about, we can pick any epsilon we want as long as it's positive, but the kind of the oomph behind it comes from thinking about epsilons being really, really small. We can pick epsilon as small as we like. How close do we want our estimator to be to the true value? We could pick it as small as we want, and as n goes to infinity in the limit, the probability that it's less than whatever distance we come up with is going to be 1. Okay. So the idea here is that as we get more data, that's the n goes to infinity part, the statistic approaches this true value there. So we're getting closer and closer to this thing that we're really trying to measure. This relationship here between the statistic G and the unknown value gamma, this comes up over and over again, so it has a name. This, I could also say this as statistic G of X converges in probability to gamma, or we might write it as G of X converges in probability to gamma. So this little arrow sign with a P over it, we would read that as converges in probability. So consistency, this property that we'd like any estimator to have, has the idea of convergence and probability built in to it. But the kind of the main idea here is that consistency means that as we're getting more and more data, the statistic is probabilistically becoming closer and closer to its true value. Okay. So, emphasizing a point here. Consistency is highly valuable, highly desirable for any estimator. Any statistic that we're going to calculate and do inference from, the things that we want from it are, first, that it's unbiased, and second, that it's consistent. Does it systematically hone in on the value we're interested in? Okay, is it unbiased in the sense that it doesn't consistently overestimate, it doesn't consistently underestimate, it's just right there. That's unbiasedness. Second thing that we care about for any estimator is, as we get more data, are we getting more and more likely to be closer to the true value? Are we improving, or are we just sort of getting stuck? So those are things that are true for any estimator. The last thing I want to say in this video is going back to the sample mean as an estimate of the population mean. Okay, so consistency applies to any estimator, but I want to say just a very few words about the laws of large numbers, and they are about the sample mean. So our current statistic of interest here. And they are kind of the codification of this idea that the sample mean converges in probability. It also converges other ways to the population mean. So let's just write them down and talk about them a little bit. There's sort of conventionally think about the weak law of large numbers, and then there's a strong law of large numbers. The weak law of large numbers is basically the same idea that we just saw with consistency. It says that the limit as n goes to infinity of the probability that mn minus mu, the distance between them, is less than epsilon, equals 1 for all epsilon greater than 0. Okay, so the weak law of large numbers says that the sample mean is a consistent estimator of the population mean. It says that it converges in probability to the population mean. That is the idea there. So let's see, mn is consistent estimator of mu. Strong law of large numbers, I'm just kind of, I don't really think that it's going to affect most of your lives that much, but you'll run across it. Let's just write it down and note a couple things about it. Strong law of large numbers says that the probability that the limit as n goes to infinity of mn equals mu. So the probability of this event equals 1. Okay, this is a different kind of convergence. The weak law of large numbers and the idea of consistency are based on convergence in probability. There are other kinds of ways to think about something getting arbitrarily close to another thing when there is randomness involved. Okay, so limits are already kind of tricky things to wrap your brain around, and once you add random variation in there, figuring out what's happening in the limit gets harder, and there's, as I just said, there's multiple ways to do it. The kind of convergence that is present in the strong law of large numbers is called, we would say it converges almost surely, or sometimes people say converges with probability 1. Am I right? And converges almost surely to mu. For most social scientists learning statistical methods, the difference between these different flavors of probabilistic convergence is not going to really matter much. There's other types of convergence as well. There's like convergence in mean square, which is actually what we showed when we derived the sample variance and observed that it, sorry, not the sample variance, the variance of the sample mean. We derived the variance of the sample mean and showed that it went to 0 as n goes to infinity. That would be called convergence in mean squared. So different ways to prove that as the amount of data goes to infinity, the statistic you're calculating from the data is getting arbitrarily close to the thing that you're trying to measure. You might guess from the names that it's easier to prove convergence in probability than convergence almost surely. It's also true that if something converges almost surely, or it converges in the mean square, it will definitely converge in probability, but not the reverse. Something can converge in probability and not converge almost surely. Like I say, that's this is not going to be a big part of your methods education going forward, unless you really want to take kind of the I want to be a methodologist route and you want to be taking classes in the statistics department. Then this is something you might want to brush up on. And honestly, if you're interested in getting on that track, in preparation for that, taking math class and real analysis, that's a class that involves lots and lots of limit taking, would be good, kind of a good stepping stone to that. The takeaway points though, for 200A here on this little lesson in basic asymptotics here. First of all, that the sample mean is a consistent estimator of mu. Okay, so as we get more data, it's probabilistically getting closer and closer to the true value. And second takeaway point is this whole idea of consistency. Consistency, like unbiasedness, is a desirable property for any estimator, any statistic. We like our statistics to continue to get better and better as we give them more and more data to work with.